All right, back with segment 2 for chapter 3. We left off with mole to mole conversions. And so here what we're going to do is just look at the relationship for moles. So we can use a chemical formula to relate the amount of each atom to the amount of a compound. So here we've got little molecules of water. And so we can see that there are going to be several different relationships. For instance, we can say we have 2 moles of hydrogen is going to go into 1 mole of water, and that's based on that subscript 2. We could also say we have 1 mole of oxygen in 1 mole of water. Or we could say we have 2 moles of hydrogen for each mole of oxygen. All right. So we can also use these on the atomic scale. In other words, we could say 2 atoms to 1 molecule, 1 atom to 1 molecule, or 2 atoms to, well, that should be 1 atom, right? See a little typo right there. All right, so stoichiometric equivalences. So stoichiometry is the key to all of our chemical reactions. Whenever we have chemical compounds, we'll be looking at the moles of the atoms. They always have to combine in those ratios. And then, of course, when we look at formulas in a reaction, the ratios there have to balance out as well. So the ratios allow us to convert between moles of each quantity. So in other words, what we're going to be able to do with stoichiometry is look at the mass to mole and then mole to mole relationships. In essence, what this does is allow chemistry to compare A to B. So we always hear you can't compare apples to bananas. Chemistry said, but that's not true. We can just do it by count. So an example would be N2O2. For this, we can look at 2 moles of nitrogen go into 1 mole of N2O2. There'll be 5 moles of oxygen to 1 mole of N2O2. And then, of course, we can have 2 moles of nitrogen to 5 moles of oxygen. So your equivalency then would be 2 moles of nitrogen is equal to 1 mole of N2O5, and that of course would turn into 2 different ratios for us. We could do 2 moles of nitrogen over 1 mole of N2O5, or we could do 1 mole of N2O5 over 2 moles of nitrogen. So don't let this kind of confuse you at all. All we're literally doing is setting up conversion factors. Okay, so I set up the equality based upon the formula itself. We have 5 moles of oxygen, and instead of having an arrow here, we could just say is equal to 1 mole of N2O5, and that would give me the 2 potential conversion factors. Okay, and of course we can do that for all 3 of these. Now, calculating the amount of compound by analyzing one element. So here, what we're going to do is look at a sample problem here. Calcium phosphate is widely found in natural minerals, bones, and some kidney stones. A sample is found to contain 0.864 moles of phosphorus. How many moles of calcium phosphate are in that sample? All right, so what is it we're trying to find? Okay, well, we want to know how many moles of calcium phosphate are in the sample. And of course, what we know is that we have 0.864 moles of phosphorus. So that means we know, according to the formula, that for every 2 moles of phosphorus, we're going to get 1 mole of calcium phosphate. So now to put it together mathematically, we're going to take our 0.864 moles, which is coming from the problem. There it goes. We have our 0.864 moles of phosphorus coming from the problem. And then, of course, our relationship for phosphorus to moles of the entire compound. So for 1 mole of calcium phosphate, it's going to cost me 2 moles of phosphorus. Moles of phosphorus will cancel out, and we'll be able to do the math here and get 0.432 moles of calcium phosphate. All right, so calculate the number of moles of calcium in 2.53 moles of calcium phosphate. I'll give you the pause here. There's your 5 potential answers. And hopefully you came up with 7.59. And again, we'll take that 2.53 moles of calcium phosphate. We know that there are 3 calciums for each calcium phosphate. And so we'll take 2.53, we'll multiply that by 3, and divide that by 1. That'll give us 7.59 moles. All right. A sample of sodium carbonate Na2CO3 is found to contain 10.8 moles of sodium. How many moles of oxygen atoms are present in the sample? So there's our potential answers. And here the answer is E, 16.2 moles. So we know how many moles of sodium we have. We know the formula for sodium carbonate. Now keep in mind on a test question, I may not provide you the formula. So don't let naming slip. You want to make sure you're ready to name all of your compounds or turn your names into formulas. All right, you want to make sure you can do that. So we have 10.8 moles of sodium. That's going to be equal to how many moles of oxygen? We know that it's going to be a 2 to 3 relationship. We have 2 moles of sodium to every 3 moles of oxygen. And so we'll just set up that ratio. So we'll take 10.8 moles of sodium multiplied by 3 moles of oxygen, cancel out our moles of sodium, and we'll end up with 16.2 moles. All right, now once we understand stoichiometry and the stoichiometric calculations, we can start to look at mass to mass calculations. These are our common laboratory calculations. So we're going to have our aspirin synthesis this week, potentially next week, depending on when you start watching these videos, or we just did it last week if you're a little bit behind. But that's what we're going to be using. We're going to be using mass to mass calculations to figure out our products and of course our percent yields, which is all part of this chapter. So we'll need to know what mass of reagent B is necessary to completely react given mass of reagent A to form a compound. So the stoichiometry comes from the chemical formula of the compounds and what that's going to look like in relationship to each other. So we're going to need to use subscripts and coefficients. Okay. The summary of the steps, I always think of it as a 3-step process. So what we want to do is go from mass of A to moles of A. Then we're going to go from moles of A to moles of B, and then finally moles of B to mass of B. So that's our 3-step stoichiometric process. All right, so chlorophyll, the green pigment in leaves, has the formula C55H72MgN4O5. If 0.0011 grams of magnesium is available to a plant for chlorophyll synthesis, how many grams of carbon will be required to completely use up the magnesium? All right, so analysis then. We have 0.0011 grams of magnesium, and we want to know how many grams of carbon. Again, we're going to have a 3-step process. We're going to figure out moles of magnesium from our grams of magnesium. Then we're going to relate moles of magnesium to moles of carbon. Finally, we'll take that mole of carbon and turn it back into a mass, and we'll have a mass of carbon. So assembling the tools then, we'll go to our periodic table. We know we have 24.305 grams of magnesium for 1 mole of magnesium. We know for every 1 mole of magnesium, it's going to be 55 moles of carbon. Now, where did that come from? Remember, that came from up here. We have 55 to 1. So 55 carbons to 1 magnesium. And then we know for every 1 mole of carbon, that's going to be 12.011 grams of carbon. So again, 3-step process. Grams of substance A, we're going to need the molar mass of A to get to moles of A. We'll use the chemical formula in this case. Later we'll see we can use the chemical reaction to get moles of B. From moles of B, we'll use the periodic table and the molar mass of B again to get grams of substance of B. So we're going to start with 0.0011 grams of magnesium. We're going to use our molar mass, 24.305, to calculate moles of magnesium. Then we're going to use our chemical formula to get from moles of magnesium to moles of carbon. And then we're going to use our periodic table again to get from moles of carbon to grams of carbon. So we'll start with 0.0011 grams. We'll divide by the molar mass of magnesium. That's going to allow our grams of magnesium to cancel out. We know that moles of magnesium to 55 moles of carbon, so moles of magnesium will cancel out. We now have moles of carbon, and we're going to use our periodic table and our molar mass to make moles cancel out. That leaves us with our grams of carbon. And if we run that through the calculator, we get 0.030 grams. So if I start with 0.0011 grams of magnesium and I want to use it all up to make chlorophyll, I'm going to need to have 0.030 grams of carbon. All right, How many grams of iron are required to use up all of the 25.6 grams of oxygen atoms to form Fe2O3? So there are 5 options. All right, hopefully you paused it and now you're starting to go forward again. If not, pause now before I give you the answer of 59.6 grams. Now, how do we do it? Again, it's a 3-step process. Mass of oxygen to moles of oxygen, moles of oxygen to moles of iron to mass of iron. We're going to start with our 25.6 grams of oxygen. We know that there's a relationship of 3 to 2 for moles of oxygen to iron. So we're going to take 25.6, divide by the 16. Grams of oxygen will cancel out. Moles of oxygen will cancel out. We know that we're going to have 2 moles of iron for every 3 moles of O. And then again, moles of iron will cancel out by multiplying by the periodic table. And that's how we got the 59.6 grams. All right, silver is often found in nature as the ore argentite, Ag2S. How many grams of pure silver can be obtained from an 836 gram rock of argentite? All right, here's your pause. And hopefully you came up with B, 728 grams. And again, same 3-step process. You might get bored of that, but it's going to work every single time for us. We're going to start with 836 grams of the Ag2S. We're going to go to grams of silver. We're going to do that by looking at the mole-to-mole relationship and, of course, our periodic table. So we'll start with 836 grams, divide that by the periodic table of 247.8. Moles will cancel out when we look at the formula, the chemical formula relationship of 2 to 1. And then we'll multiply by the periodic table for silver at 107.9. Moles of silver will cancel out. That's how we came up with 728. All right, now another thing we can do with chemical formulas and mole relationships is called percentage of composition. So it's a way to specify the relative masses of each element in a compound. So what we'll do is we'll list off by percentage the mass of each one. So we have percentage by mass. So the percent by mass of an element is equal to the mass of that element divided by the mass of the entire sample times 100%. So it's a simple percentage. Sodium carbonate then is going to be what? Well, 43.38% sodium, 11.3% carbon, and 45.29% oxygen. Now, if I sum up all those percentages, what should it be? Well, it should be 100%, right? All right, so let's take a look at how we're going to do this. Let's determine the percentage composition based on chemical analysis of a substance. A sample of a liquid with a mass of 8.657 grams was decomposed into its elements and gave 5.217 grams of carbon, 0.9620 grams of hydrogen, and 2.478 grams of oxygen. What is the percentage composition of this compound? Now, to do the analysis here, we're going to calculate the percentage by mass of each element in the sample. So our tools here will simply be the equation by percent mass. We know the total mass. We are told the mass of the liquid was 8.657. Now what we're going to do is take the mass of each element and simply do by percentage. So for carbon, we're going to take the grams of carbon divided by that total times 100%. So we're going to take 5.217 divided by the 8.657. That gives us 60% carbon. For hydrogen, we'll do the same formula, but we'll do the mass of hydrogen over the total. So we have 0.9620 divided by 8.657, our total mass. That's going to give us 11.11% hydrogen. Finally, for the oxygen, we'll now use the mass of oxygen and use the same formula. And that's going to give us 28.62%. Now, if we did everything right, this should sum up to 100%. And here it comes up to 99.99, which is going to be close enough for government work, right? All right, percentage composition tells us the mass of each element in 100 grams of substance. So in 100 grams of our liquid then, we can now look at the percentages and say we have 60.26 grams of carbon, 11.11 grams of hydrogen, and 28.62 grams of oxygen. All right. A sample was analyzed and found to contain 0.1417 grams of nitrogen and 0.4045 grams of oxygen. What is the percent composition of this compound? The first thing we want to do then is calculate the total mass of the sample. So we're going to take our two components, we're going to add them together and get our total mass, which is going to be 0.5462. Next, we can calculate the percentage of each of those pieces. So for nitrogen, we'll take our mass of nitrogen, divide by that total, times 100%. So according to the question, we have 0.1417 grams of nitrogen. We're going to divide that by our total mass that we just summed. That's going to give us 25.94% nitrogen. Next, we'll do oxygen. Following that same pattern, we'll take grams of oxygen over the grams of total. That'll give us 0.4045 over the total mass, which is going to be 74.06. Now, of course, if you wanted, you could have just taken the 25 and subtracted that from the 100. And we should have arrived at the same 74.06, right? Now, on a test question, typically what I want to see is everything written out like this by each component, and then maybe a sum at the end to make sure you have 100%. So if you're being asked for the percentage of each component, make sure you're taking in the mass that's given up here in the questions. Okay, don't actually do it by subtraction, but in a lab to verify yourself, you might have done it that way. All right, in a previous year turn slide, you found that an 836 gram of argentite contains 728 grams of silver. What are the percentages of silver and sulfur by mass? Now, a question like this would lend itself to that possibility, right? You could take the 728, that's how much silver is in that thing. You could divide that by 836, which is the total, get that percentage, and then just subtract from 100 to answer this question. Hopefully you came out with E. So again, you could do it individually. So we would take 728, that would give us the 87, and then simply subtract the 87 from 100, and that would give us 12.9. All right, percent compositions and chemical identity. So what do we care about these percent compositions? It's because we can use these to figure out our theoretical or even calculate the percent composition of a compound. So we can do this for molecular or ionic compounds, it doesn't matter. Okay, so we can do it for either, and the method will be the same. Okay, it will also let you distinguish between multiple compounds formed from the same two elements. So in organic chemistry, this becomes very convenient because a lot of times we look at what's called an empirical formula. We'll be discussing this a little bit, and we can burn a substance and figure out what the percentages are of carbon, hydrogen, and oxygen, and that will give us our multiplier. Not necessarily tell us what is there, but at least tell us the ratio of what's there. Now, if the experimental percent composition is known, right? So calculate the theoretical percentage composition from proposed chemical formula. So in other words, I discussed before doing elemental analysis in our labs for phosphorus, carbon, oxygen, hydrogen, nitrogen. I think I said phosphorus already. And so we would send them off to a lab and then they would come back and tell us what the percentages are. Well, up to that point, we had used the formula to know our theoretical percentages, which is what we were just looking at. Then when we get the experimental composition, we could then compare those two, right? So nitrogen and oxygen can form multiple compounds. So N2O, NO, NO2, N2O3, N2O4, and N2O5, these are all stable formulas. So if I'm trying to synthesize, let's say N2O5, I can calculate the percentage of what it should be, then send my sample out for analysis. They'll send back what the percentages are, and I can see if they match up. Okay, so we can use percent composition then to give us an idea of whether or not we're on the right track with our synthesis. Let me see, are the mass percentages 30.54% nitrogen and 69.46% oxygen consistent with the formula N2O4? So again, we've sent our sample out to the lab. They sent back that it's 30% nitrogen and 69% oxygen. We believe the formula is N2O4. So now we can calculate what the percentages for N2O4 should be and then compare them to what we actually know. Now, what we'll do is we're going to assume we have 1 mole of the compound, right? So if we assume we have 1 mole, then we should have 2 nitrogens and 4 oxygens. So the subscripts will tell us how many moles are there. So we'll say we have 2 moles of nitrogen and 4 moles of oxygen. Now we can go to our periodic table and get our molar masses, right? And we'll determine the mass for 1 mole of this material. So the molar mass of N2O4 then would be 92.14 grams of N2O4. Now we're ready to calculate the percent by mass for each element. We know how many moles of nitrogen should be there. We know the total mass of that percentage, right? And we can do the same thing for oxygen. So we know that we have 14.07 grams of nitrogen per mole, and we have 2 moles. So that should give us 28.14 grams of nitrogen. We have 4 moles of oxygen, so that should give us 64 grams of oxygen. Now we can do our percent composition. We have 28.14 over the total mass of 92, and that tells us we have 30.54%. We have 64 for oxygen over the 92.14 total, and that gives us 69. And so in this case, our experimental values match the theoretical percentages for that formula. Now, if we thought we had a different formula, then again, we would find out, uh-oh, something's wrong. We don't have the percentages from the experiment that we thought we had in the theoretical. Now, if a sample containing only phosphorus and oxygen has a percent composition of 56.34 and 43.6, is this potentially P4O10? So again, what we'll look at is the relationships. We have 4 moles of phosphorus for every 1 mole of P4O10. And we have 10 moles of oxygen for every 1 mole of P4O10. So 4 moles of phosphorus would equal 4 times 30.97. That's coming from the periodic table. That gives us 123.9 grams of phosphorus. We have 10 moles of oxygen at 16 grams per mole each, gives us 160 grams of oxygen. We sum that up and we have our total mass. Now we can take each one of our components, right? So we can take phosphorus and oxygen and independently compare them to the total. So for phosphorus then, we have 123.9 divided by 283.9 times 100%. Tells us we have 43.64%. We take 160 divided by the 283.9, and that gives us 56.36%. At this point, we can see our percentages are pretty close, right? So if a sample containing only phosphorus and oxygen has a percent composition of this and this, is this P4O10? Now they say no, but that's pretty close, right? Oh no, it's backwards. Look at that. It's 56 versus 43. Tried to trick me there. 43 oxygen to 53, or excuse me, 56 oxygen. So they're actually reversed, which means we know that that can't be the right formula then. All right, so determining empirical and molecular formulas. Again, we'll use these same ideas, but what are these things we're talking about, empirical formulas and molecular formulas? Molecular formulas we've studied already. We know what molecular formulas are, but what is an empirical formula? All right, when making or isolating new compounds, one must characterize them to determine the structure and present the empirical formula. Now, the empirical formula is the simplest ratio of atoms of each element in a compound. So, for instance, if we had C2H4, we wanted to give the empirical formula, it would simply be CH2. So that's why earlier we said a lot of organic compounds will give us the exact same empirical formula. Okay. Now we can get the empirical formula by analysis. And so we'll burn our formulas, we'll burn our substance and see what the products are and work backwards to get the empirical formula. The molecular formula is the exact composition of one molecule. So the empirical formula is the reduced formula. It's as low as you can go. It's always the least common multiple. The molecular formula is the exact whole number ratio of atoms of each element in the molecule. So for instance, glucose, the empirical formula is CH2O, but its molecular formula is C6H12O6. So you can see how that reduces down to the lowest common multiple. Now there are three ways to calculate your empirical formula. One would be from the masses of the elements. For instance, you literally know how much of each item is in there, and you can calculate the empirical formula from that. If you know the percentage composition, so again, we were just studying these theoretical versus experimental percent compositions. So when the experimental composition comes in, you could use that to calculate your empirical formula. Or if you're working with hydrocarbons and organic chemistry, a lot of times you're going to get it from combustion data. And so you're going to take your compound, your unknown compound, and you're going to literally burn it. And then it's called scrubbing. You're going to scrub it out to get the different elements. This is going to give you the masses of combustion products. Now there you'll have to work backwards because you have the combustion of this much of a sample will give the compound CHNO and pure oxygen to give this much CO2 and this much water. And so knowing how much carbon and hydrogen is there, you'll use your grams of CO2 to figure out how much carbon was there and your water to figure out how much hydrogen was there. Now we're going to look at all three. So first we'll determine by the mass in grams of each element. Convert the mass into grams of moles, then divide all the quantities by the smallest number of moles to get the smallest ratio of moles. Then we'll convert any non-integers into integer numbers. So if your number ends in a decimal equivalent of a fraction, then you'll multiply all quantities by the denominator of that fraction. Otherwise, you'll round numbers to their nearest integer. So let's take a look at a problem. When a 0.1156 gram sample of a compound was analyzed, it was found to contain 0.04470 grams of carbon, that much hydrogen, and that much nitrogen. Calculate the empirical formula of the compound. So again, the first thing we'll do is calculate the moles of each substance. And actually, I just happened to glance down, and I think this is probably a good place to pause. And so we'll stop the segment here, and then we'll make segment 3 begin with looking at how we're going to go through the strategies of these empirical formulas. So I apologize for running a little bit long here. We're at like 26, 27 minutes. And again, so we'll pause it here, and on the next segment, we'll go through these calculations. So if I got you wanting to know, then go ahead and obviously click on to the next segment, and we'll pick it up in segment 3. All right, see you in a bit.